Hi everyone, thank you for coming. So it's my pleasure to introduce Rachel Smith. She's the head of the Astrophysics and Astronomy Laboratory and the Meteorite Curator at the Museum of the North Carolina Museum of Natural Sciences. She's also associate professor at the Appalachian State University and adjunct professor at the University of North Carolina, Chapel Hill. And she will be talking today about young stellar objects, and in particular carbon and oxygen isotopic measurement, or YSO. So thank you for coming, Rachel.
Hello. Oh, I think I did it. Okay. Thank you, everyone. Thank you, and thank you, Pierre. And it's been a great day. So thanks, everyone, for coming to the talk. I hope I've added more slides since I've talked to people, because everyone has different interests, and it's been a lot of fun meeting everyone here. So thank you. And I'm going to turn this on. I'm really bad with laser pointers, so stop me if. Okay. So I'm going to talk about the title of my talk is Temporal Variability in Young Stellar Objects and Implications for the Early Solar System. And I just put on, I work in a museum, and so my lab is kind of an unusual lab, which is visible to the public. And so we have these glass walls, and so we're always challenged to showcase what we're doing. And astronomers, what we do typically, as you all probably know, is we stare at our computers most of the time, and that's typically not that interesting to look at, or maybe we're doing it wrong. But anyway, I'm on this project with the American Museum of Natural History called Open Space, and it's a NASA-funded project. We're in our 5th year to create visualizations using data sets. And so if any of you are familiar with you've probably heard of the Hayden Planetarium in New York, and they have something called the Digital Universe, which is a whole repository of data taken over many decades from missions and from various telescopes. And so everything flying through the universe, it's interactive, it's open source, and everything is based on real data. So this is, I just put on some visuals to show some of what is possible. And these are exoplanets. And so just a little movie that one of my students made for one of the fly-throughs. So if anyone's interested in it, you can ask me later. I have a few other little clips, but I just like to mention it. And it actually is helpful for talking about research, especially for different kinds of audiences. And I just think it's kind of pretty. And since we're in Arizona, I put on a fly-through of a flyover of the Grand Canyon. And I did that with my collaborators on here. So on this project, Adwin Bugart, who's at the Infrared Research Telescope Facility at University of Hawaii, Jeff Blake, who's at Caltech, and Klaus Pontoppidan, who's at Space Telescope. And they are collaborators on these observations. All right. So one thing, I know this is a mixed audience, so forgive me if you already know everything I'm going to say. For those of you who are not familiar with young stellar objects, these are forming stars with disks of gas and dust around them. And from them, planets will form, most likely. And so this is just actually took this from one of my class slides that, this is like a little life cycle. And so we're kind of at this stage here when we do our observations. And so this would be class 1 or class 2 objects where you have an embedded disk in an envelope, or you have a disk that's blown off most of its envelope. And so we're looking at these infrared objects along a single line of sight, and I'll show what that means in a second. And so this is the material that planets will eventually form from, most likely. And I'm focusing on carbon. I'll talk a little bit about oxygen, because we're looking at CO. And so this is, we're really interested in the early protoplanetary chemistry. So we're trying to understand certain aspects of this early chemistry before the planets form. Okay, so line of sight. So I realized when I gave this talk once before to a mixed audience that they weren't sure what a line of sight was. So I just have a little very bad animation that I made. This I did not make. This is good. But this of showing what line of sight. So we're looking in the infrared, and this is IRTF. So this is the telescope in Hawaii that I'm using now. And so this is a single line of sight through an artistic rendering here, an infrared source, an infrared target of forming star, and around it, in very sped up time of about 1 million or so years, planets will form from the gas and the dust. And so line of sight, these are CO molecules, not to scale. And just making sure you know, I know that. I know you know that. And so they're all lined up on this. So we're looking at a a pencil beam, some astronomers sometimes call it. We're not looking at the bulk disk, but a pencil beam. And from the absorption, we get molecules along the line of sight will they have different energies, and so we're probing the near infrared. And so we have two band passes, the 4-micron pass and the 2-micron band pass. And so it's a single vibrational transition with rotational lines that are now spread out across the single vibration. So this would be a 0 to 1 transition. So the ground state to first vibrational state, actually it's going up in energy, 0 to 1, and then the overtone, which is higher energy, which is 2 micron, to get one of the more abundant isotopologues. So that's my little animation. Okay, so young stellar objects, there's really snapshots in time, as many of you know. And essentially for protoplanetary disks, these evolve over, an order of several 100,000 years to several million years. And eventually you get dissipation of the circumstellar envelope and accretion of the disk. These are important analogs. We treat them often as analogs of understanding the physical and chemical processes leading to planets. But we have to remember that our observations, astronomical observations, are single moments in time for these objects. The nice thing about CO is that we get high-resolution observations, and these have been used to understand solar system anomalies. And in order to understand solar system anomalies, we need this high resolution because we're comparing the data to meteorites, which are at very high resolution. A lot of you work on meteorites, and so the precision on mass spectrometers is orders of magnitude higher than what we get with telescopes. And so we need the highest resolution we can to really get precision in the data. This happens to be, I used Keck for this looking at, I was excited to look at the galactic center to try to get isotope ratios from, this is GCS3, which is about 40 parsecs from the center of the galaxy. The black hole would be right about here, and it's really hard because it's a messy area. It's a very bright, busy area of the sky, so we really have to reobserve this. I did get some information on GCS3. Sagittarius A star, which is actually at the location very close to the black hole, didn't really work very well, and it has to do with how the telescope nods on and off the sky, and so we have to reobserve that. But just for getting isotope ratios, we do need to be able to get the spectroscopy. We're not really using images, even though we took this image here. And this, of course, is HL Tau, which we'll talk more about, which is one of the most famous T Tauri stars, and the first which has been imaged to have these lanes where we think planets might be forming. So CO, why CO? Well, there are a few reasons. The main reason is we can observe it really well, so we can probe the isotopologues of CO that we're interested in. But of course, CO is a reservoir. It's a significant reservoir, and by significant, we're talking 10 to 30% of carbon and 10% of oxygen. So it's not all of the carbon and oxygen, of course, but it's a good reservoir of it in a single molecule. And CO itself is a precursor for interesting prebiotic chemistry. And so we have formaldehyde and methanol, and there are people here who do this work of looking at this, prebiotic chemistry. What are the molecules needed for life? How do they form? And CO is just one part of that process. And so we can get an understanding, if we can try to understand what's happening in these disks, we can not only understand better how planets form, but also the prebiotic chemistry that eventually led to life on Earth and might lead to life on in other systems. And that's the big arm-wavy astrobiology connection with the YSOs, because we can't really say anything, of course, about life in any of these systems or their chances of forming life. I get this, of course, maybe not here, but in the museum, they think that we say prebiotic and it's like we're looking for life, but we're not. So anyway, so CO is a really important molecule, and so we use this to understand various aspects of the chemistry. So and I'm going to talk about several things, so I'm not going to cover in detail a lot of this, but I will bring in two anomalies that we have been looking at in connection to the solar system. And one is the solar system carbon isotope anomaly, and that the anomaly, here's 12C, 13C, measured with various molecules. This is from Malam et al., which I forgot to put I should have put the paper. Malam et al. 2005, is looking at the carbon. This is galactocentric radius, so this would be the galactic center. This is about where the solar system is. And the 12C, 13C in the solar system is about 89, and the interstellar medium is 65. And this is measured to within error, so we think this is a significant anomaly. And so one way to start to try to understand that is, what do we see at 8 kiloparsecs in YSOs, in young stellar objects? And I'll show some of the data we have. Because if we're going to assume maybe this is galactic chemical evolution, like we just get more 13C over the evolution of the solar system to bring down this ratio from 89 to 65, by increasing 13C, we should expect YSOs to be kind of right around here, but we don't see that. We see a spread, and I'll show you that in a second. So that's with carbon, we can look at massive YSOs with 12CO, 13CO, because these are abundant isotopologues. With oxygen, it gets a little more tricky. So here's oxygen, and many of you, so delta-delta plots are probably familiar to some of you, but maybe not all of you. And so cosmochemists love delta plots, delta notation, and that's essentially the formula here. This is looking at CO looking at oxygen, and the main point here is looking at CO self-shielding, which I'll talk about in a minute. But the axes, if you're not familiar, IO would just be 18O or 17O, so 17O on the y-axis, 18O on the x-axis, divided by your standard. So say this is 17O, so you have 17O, 16O of your sample, or your YSO, 17O, 16O of your standard mean ocean water, which would be your standard, times 1,000. So it's looking at small changes spread out over, instead of percent, it's like per thousand. So that's my very two-sentence definition of, now we all understand the three isotope plot, okay? So, so this has been used, this is from McKeegan et al., this general overlaid with this self-shielding, but this is from McKeegan et al.'s well-known science paper looking at the solar wind, and found that solar wind, which is considered this the oldest amount and the largest amount of gas we have in the solar system would be the sun. The solar wind is down on this plot, which essentially means it's got a 16O excess, and this is good news for trying to understand the spread in meteorite data here along this line called a slope 1 line. And essentially what this is saying is that if maybe there's a process called CO self-shielding that spreads out isotopes in meteorites along this line that we can't explain by just mass fractionation of the isotopes. So Earth, Moon, Mars, regular chemistry can explain how isotopes separate on a slope half line, but the slope 1 line, this is a famous anomaly that's been known since 1973, and maybe it's a process called CO self-shielding. So why am I talking about this? Well, we can look at oxygen in CO in YSOs and see, do we see YSOs plotting along a slope 1 line? And if so, maybe it's a signature for this phenomenon called CO self-shielding, which could have occurred in the early solar system. And so really quick, really briefly, what is CO self-shielding? If you've never heard of it, this may not make sense. Essentially what it means is that molecules are shielded from photodissociation according to abundance. So it's not mass related, it's abundance related. And this is just saying that C16O is so abundant in the early solar nebula that it kind of stays intact, and then the rarer isotopologues are photodissociated and they go off into carbon and oxygen. And CO self-shielding is a hypothesis of what could have happened in the early solar nebula. So we can look at YSOs to try to understand this. And so what I'll mostly be talking about today are large, bright, massive young stellar objects, which were in most cases I'm looking at carbon, but the main motivation for the early work that I did was looking at the oxygen with low mass YSOs. But today when I'm going to try to focus on variability, and that's mostly looking at, the main point of this talk is looking at how these YSOs change in short periods of time. So I'm not going to focus necessarily on one result from the low mass stars on self-shielding, but I will show those results at the end. But the idea is, okay, so what are we looking at? We're looking at the survey of molecular reservoirs to try to understand the chemistry. And we're looking at carbon and we're looking at oxygen. And in this talk, I'll talk about how some of these abundances and temperatures, which we measured at pretty high precision, are changing in very short periods of time. And what does that mean? And so we have large, bright YSOs, and the nice thing about massive young stellar objects is that we can probe more than one reservoir along the single line of sight. So we have ice and we have gas along a single line of sight for one single target. And that means that we can compare isotope ratios in CO gas, for instance, with CO2 ice, especially with carbon we can do this, and sometimes with CO ice. And so I put this in because Ilaria was asking me about winds. I don't know if you're here, but are you there? Okay, there you are. There you go. Look, winds. So we do see spectral signatures in one of some interesting conversations today with some of the astronomers here about what we see in these profiles. And I'll just mention that in the spectra, if you do spectroscopy, you realize that there are a lot of projects in one spectrum that you may not have time to do right away. And one is, I never look at these lines, so I don't really care about 12C 16O lines at the 4 micron band because I'm not going to use them. So this mess right here, which is actually pretty interesting, is this P Cygni profile, would not be easy to analyze as much as like a nice, pretty absorption line of 13C 16O. So we see these profiles sometimes, and what this is a signature of some kind of cool phenomenon happening in the massive star, like blowing. We think it's, or a paper was published where it was blowing winds out of the envelope, and they modeled this. And I don't have that slide, but it's thought to be winds from that star. And there are a lot of examples of really interesting profiles that we see in the massive stars that we don't kind of want to see if we're getting abundance information. Okay, so a single line of sight, we'll see, these are various profiles for one YSO. So this is our Keck data here. And we also, and I just overlaid randomly here, just showing that we have CO2 ice, 12C, 13C from CO2 ice. We do get 12C, 13C from CO gas. And in this particular source, we actually also get 12C, 13C from CO ice, which is very hard to get. There are only a few targets where you can get 12C 16O ice that's not saturated, that's not too deep, with 13CO ice as well, because 13CO is much weaker in the ice phase. So you have to, there are only a few targets where you have that balance of not being too much and not too little. So we don't have too much data on that. So now I've started to use iShell, which is a high-resolution spectrometer, 80,000. And the higher, you want a higher number here. For non-astronomers, we want a higher number. The higher number, the better. With CRIRIS, with VLT, which we, the very large telescope, which we looked at the low mass stars, it was about 95,000. So that was the best. But 80,000 is good enough to resolve the line profiles. And this is actually an image from our camera. So I put it in there. It's small and little, but it's mine, so I put it in. And you can see this is a temperature gradient. It's very tiny, but this is S140 Iris-1, which is a massive YSO, and some other little star here. And we just got the data, so I don't have those results yet. But talking about variability, so that was kind of more of an intro of why are we doing this? What kind of questions are we asking? Like what's happening with the early solar system? How can we understand planet formation? Now I'm going to just shift a little bit and talk about variability and what that means, because that's kind of the focus of this talk and is an inspiration for a new kind of investigation that I've been working on. So the YSOs have been observed for a long time to be variable. So we think of young stellar objects evolving over these very long time scales, but actually they've observed to be variable in certain parameters from weeks to months, and we see this too in some of the data. So here are some examples, and I'm just going to mention a few examples. They're not all of the examples, but for example, 10 to 60% at all infrared wavelengths at a big YSO survey done by some of these studies here. Possible, and I'll go through some specifics in a second, but possible drivers of these, what drives some of this variability? Well, you could get structural changes in the disk over short periods of time, infalling of material, influence of a companion star, and some of you, I know we were talking about photoevaporation on some of the disks, magnetic field changes, and X-ray flares are just few of the very short-term phenomena that could affect the disks. These can be periodic or chaotic, which is kind of interesting. It's been thought that there's greater amplitude in variability for embedded targets, so maybe that means that at an earlier stage of evolution, there's more stuff going on, whatever that is, and this has to be modeled. But you also see variability in evolved disks. So there's not a consistent, from what I gather, there's not a consistent explanation of what causes variability and how to really classify certain objects as being certain kinds of variable. It looks like to be just a lot of different types of variability, and trying to piece that together into one big picture is a challenge. And so my question is really, are carbon reservoirs affected by the variability? So quantifying, how does this affect column densities? Because we use these column densities and consequently the isotope ratios to try to explain certain phenomena. So if these are changing, what does that mean in our interpretation of the data? So just some examples from the literature. We all know HL tau, probably it's very famous, and this is an ALMA image just tracing out some of the lanes here, and this is just a plot of some of the magnetic field lines from Stevens et al. 2014. This was showing magnetic field effects on accretion. The fields were randomly aligned, they thought, and they said this should be considered for models, which is the typical observer's way of like, go modelers, take my data and model it, and tell me what it is. And the gaps in the disk suggest formation of planets, maybe pebble growth, which is a big topic now, or maybe some variation in dust properties, and that could be a lot of things. Some other examples, so Colette Salek in 2019 published a variability in water emission, and you can see using different instruments. So this was Gemini with Texes and Michelle. You see no emission here and emission in these profiles, and they determined this was not an artifact of the data reduction, but maybe possibly due to, again, physical changes in the disk could affect temperature or settling of material. We know that ice will sublimate, for instance, in the CO work that we're doing, so maybe there's something affecting the solid reservoir, perhaps, and maybe in the water. Chemical changes could reduce water abundance, so you get photodissociation, or you get dimming from one arm of the disk, perhaps. And changes, you get changes in gas excitation levels, so maybe we're just, you know, you get temperature changes, right? So if you have hotter, you know, some kind of a photodissociation effect and it's heating up the water, you're going to see more emission because there's more excited water molecules.
Do you know what transition of water that was?
Let me see, what transition and what water? 12 micron. No, only that it's 12 microns, so I'd have to.
I just wondered how high up it was in the energy level diagram.
Oh, what rotational transit? I'm not sure. That's a good question. I don't know. Coco, do you know?
It's about 2,000 Kelvin.
Oh, okay, 2,000 Kelvin. So very hot. Yeah, they do a lot of the. This is all. Most of this is inner disk type material. So yeah, very very hot. Different than the CO that we're looking at for sure. Different region. Sorry. Okay. Another interesting example, here they showed just over 1 week, you can see the changes in the line profiles. I just kind of like to look down here and you can see how it changes over, and this is a study looking at evolved disks. So you can see this is in just one wavelength at each frame, but you can also spread out the spectral energy distribution and see that there's significant differences. And you can see similarities across a single cluster. So in this study, they were talking about how variability is probably common. Even though they see it in certain types of stars, they also see it across a cluster, and therefore this isn't just a localized phenomenon or a certain type of star. My shifter doesn't want to work. Why don't? Yeah?
So for those of us who aren't astronomers,
oh, yeah.
like myself, how much of the object are you actually resolving in a spot like this one on the left here?
So this would depend on the spatial. This is probably not spatially resolved either. This is all the spectral work is not. So how you're talking about like the column density along the line of sight, or?
No, I mean I think in very like microscope
yeah.
ways, right? And so I think, okay, well, are you measuring the whole object? Or
right.
Are you measuring points along the object? So when you talk about variability, is it the entire
right.
object that's varying, or are there
right.
things, right, radially or somewhere along that?
Right, so that goes back to the pencil beam line of sight. Okay. So all we can say, at least for absorption, the emission is different kind of model, so I'd have to go back and see how they interpret that spatially. But for absorption, at least, it's that pencil beam line of sight. So they call that a pencil beam because it's literally what's happening in that pencil beam that's varying. So stuff is coming in, stuff is going out. So you're not looking at the bulk at all. You're just looking along that one line of sight. That's for absorption. So that's all I can. So so it's not like the entire disk is changing, just your line of sight. Something's happening along that. So something's happening in the disk, but it's not like the entire column density of the whole disk is changing, for example. Or that the whole thing is becoming hot and then colder, something like. Does that kind of answer?
Yeah, I think so. Yeah.
It's not the whole disk. So when I was showing those slides of like looking at the telescope and all the little molecules, you're really looking along this single. At least for absorption, that's the advantage of absorption, because you can compare anything you see in absorption for a single target is along that single line of sight. If it was emission, then you can have the light coming in from any place that your telescope can reach. And so then you have to do some kind of you have to do a radiative transfer model and figure out where you're looking and where that's coming from.
Okay, but the disk is rotating, right?
Right.
Right. So.
Oh, so you're saying, like, is it the variability from rotation, like, or it's?
Yeah, I don't know. I'm just asking because we talk about these kinds of things when it affects chemistry, right? So.
Right. I think that's the question: is what is causing these changes? And they don't. I don't think there's a single answer. It's like all of these different phenomena, but it's what seems to be unusual, or at least the interpretation is like we don't know what's going on, is what could be happening in the disk to affect these dramatic changes, like many tens of percent. But it's a good question. It's hard to spatially, I have to always remind myself too, is that we're not spatially resolving these at all. All we can say is with spectroscopy, at least, when we don't have a map of the object, is we can tell you the temperature. I can say the temperature of the gas, and we can infer where we're looking. Generally speaking, like an integrated line of sight. If this is hot gas, we're integrating, we got mostly close to the star, and cold gas would be far. So yeah, it's not that satisfying an explanation. Oh, no, I know. Yeah, no, it is hard because we're not spatially making big claims, it's hard to kind of spatially put it together. No, I agree.
I don't know, I mean, I resolve a lot, but people criticize me for not looking at the bigger picture.
Oh, so okay. Well, you're in good company here. So yeah, I have nothing to say about the big picture. If that, we can jump to that conclusion right away. So this is a T Tauri X Lupi is a rapid outburst. This is a famous star for having outbursts, and it's thought that maybe these outbursts could lead to column density changes in OH and H2O. So maybe some of the changes that we're seeing in the YSOs, which we haven't connected to anything physical in these specific YSOs that we're looking at, could be due to maybe some outbursts. And just jumping to new, types of observations, if you connected different types of observations together at the same time, you could say maybe if there's an outburst event when you see a column density change, then of course you could piece together some kind of picture. But we don't have that yet. And then affecting snow lines. So we're interested in snow lines, which kinds of planets are evolving, are forming where in the disk. And so if this affects if these types of changes affect snow lines and dust sublimation radii, that certainly would affect certain kinds of, or could affect, I guess, the evolution of planets. And that's a big question, right, is how do these short-term changes affect long-term disk evolution? And there isn't an answer that I think exists yet on that. And one interesting study on DR tau is that they found that a change in accretion luminosity of factor of 2 didn't affect water abundance. And so they have, they show a big change in luminosity and not a big change in water abundance. And so this was one example that showed that photochemistry and it could be, the end conclusion was that heating of deeper layers in planet-forming regions could be slow and have a longer-term effect, whereas photochemistry in the disk atmosphere would be fast, and you'd see very quick changes in your luminosity. And this was just trying to interpret, if you don't see effects in a short period of time, what could that mean? And so a lot of this is sort of trying to have an understanding for lots of different types of variability. And there's just one slide of a study which showed all these different types of variability. So you have various classes, chaotic and regular variability, so there's no single type of the way these YSOs vary, and this is just showing that kind of in a collage. All right, and finally, just an interesting as far as like the types of work that can connect to what I'm talking about. So this is a paper in Revision by Sasha Crote and authors in University of Hawaii. And what they're talking about here, and this may be, so illuminate everyone, hope all the cosmic chemists should wake up now and look at this slide. So basically the idea here is you have big delta 17 is just essentially how much does the small delta, how much does 17O change? If you get a lot of variability in big D 17O, that shows that in the 3 isotope plot, you get a lot of change in 17O, 16O essentially. And the idea here is that you see a lot of variability in big delta 17 for much less evolved components of meteorites. And the conclusion that Crote et al. Have come to is that due to the fact that these very early primitive components of meteorites have a lot of scatter or a lot of variability in big delta 17, shows that they interpret this as meaning that they could have inherited some of this variability from the solar nebula and not from the disk. And so this goes to the argument of where would self-shielding happen if it happens at all in the disk. And they're arguing that due to the variability that they see, signatures, all the signatures of heterogeneity and self-shielding could have occurred in the molecular cloud versus the disk itself. And this is actually a big argument in the cosmic chemistry. You may say, well, who cares? But don't say that to these guys, because they will argue about this forever, of where did self-shielding happen, if it happened at all. And so the interesting thing is, can we connect, we don't have observations now to connect YSOs to these components of meteorites. And so when I was talking to Sasha a few weeks ago, it'd be interesting, if we can come up with, it'd be interesting to be able to make some kind of observational connection. And right now, just looking at variability is one way to say, well, if we have variability here and variability here, maybe we can say something about the early solar nebula. But really, there are no observations that tell you in these disks that you're looking at CAIs, or not that I know of, or these early very early meteoritic-like components. So this was just kind of an interesting solar system connection to variability and heterogeneity in these isotope ratios. Okay, so getting back to, what time do I go to, by the way, just so I keep on time? Huh? No. Oh, yeah, half an hour to talk to you're like, just one more half hour, it's fine. No. Okay, so just as an introduction to these observations that I'm working on. So again, the single rovibrational band. We have, when you see R4, R3, or P, these are just rotational transitions. We can zoom in and get really nice data here to isolate the lines and calculate abundance. We have low to mid J lines. These are the isotopologues we're interested in. These are all stable the isotopologues of COs. So we have 12C16O, 13C16O, 12C18O, 12C17O. If we're very lucky, we get all of them. Usually we just get the first two, especially for massive YSOs. And then we have M band, which is this 4 micron transition, as I was talking about before. And then this K band, or the 2 micron, gives us optically thin 12C16O lines. And these are the lines we're using for our abundance calculations. We've used VLT Criris. This was early on, R of about 95,000, so really nice spectral resolution. We have really beautiful lines from these data sets, and these are all more solar type or low mass YSOs, and we're able to get oxygen and look at possible signatures of CO self-shielding with the low mass YSOs using Criris. For Keck data, and actually for IRTF, we'll have very high resolution, but for Keck, we do, how do we get the abundance is we do something called a curve of growth, where essentially we're taking the area of the line, because these are not spectrally resolved, so the line profiles are not very informative for the optical depth that we want, so we have to take an area of the line. This is done in astronomy when you don't have spectral resolution. You do what's called a curve of growth, and you essentially calculate the area, and then you plot the equivalent. It's called an equivalent width, or the W, which is the area against column density, and you fit your line broadening that way. And you figure out what is the width of the line using this technique called a curve of growth. And this is just a way to show, it's not a great way, but you basically you want the optical depth, you fit your B. And if you fit your model and you get a B value, then you can get your column density that way. It's an indirect way to get column density or abundance from the area of the line. So it's inherently less precise than measuring the column density directly through optical depth. But we can't do that even with Keck data because the resolution of the spectrograph is only 25,000. So this is too broad to be able to get that from the lines themselves. But the point here is that we just want the column density. With Criris and with iShell, we're able to get use the line profiles themselves because it's high enough resolution. In this case, we just fit a Gaussian, and we measure the column density because we can measure the equivalent. We can measure the width of the line and the optical depth, and we can pull out the instrumental broadening, and then we can get a very precise column density that way. It's really straightforward. It's really nice to do, and I'm excited to do it for iShell, the iShell data. Eventually, and then we get a total column density by assuming a Boltzmann distribution. So these are thermalized lines at the column densities. We're talking like 10 to the 17, 10 to the 18 inverse centimeters squared for column density is we plot, this is a plot of the Boltzmann distribution. So you have column density of each line divided by what's called the degeneracy, which accounts for different energy levels having the same column density essentially. Each of these dots is a spectral line, and then we fit either a 1 temperature fit by looking at the data, just saying this looks like a line, this doesn't. Here we have HL tau, which is one of the nicest spectra to analyze with cryonis. We have a 2 temperature model fitting the line, so we get a cold about 20 K, and here's about 100 K, but it varies between targets. Sometimes we get hotter and sometimes a bit colder. And these colder objects, this is W3RS5, which is a massive YSO. We think it's like the envelope or something. Although with these data, it's a single temperature, so this could be maybe disk or outer envelope combined. All right, so we get either a 2 temperature or a 1 temperature fit, and then from our total column density and our temperatures, then we can say something that this is what we're looking at, right? We're looking at the total column densities of these isotopologues and the temperatures of these lines to try to understand, what's happening in the disk, and we can get isotope ratios. So variability, this is just showing what we see in some of the data sets. So from 2012 to 2014, I'll just show a few examples. So this is a massive YSO W3RS5, which some of you are familiar with. In 2 years, we see up to 10% variation in temperature and 33% variation. These brackets just mean abundance of CO. So we're looking at 12 CO and 13 CO in this case. And you can even visually see, and this is all normalized to the continuum, so these are not continuum changes. It doesn't matter where the continuum falls, in fact, because we're looking at absorption. So it's relative to the continuum. So even if the continuum changes, we're just looking at absorption. So I care really where how deep are these absorption lines and how broad and how much do they change and affect the column density or the temperature of the gas. And similarly, S140 IRIS-1, we can see some changes from in 12C16O in a 3-year separation. So we get 13%, up to 13% in temperature, up to 46%, which is a lot, in 2 years in column density of CO. And this? All right, and then with iShell, I overplotted, because I just have the new data sets, this is the same target with iShell. So we have deeper, narrower lines, and we can resolve the line profile. Because someone was asking about this just a few minutes ago, I made a new slide just for you. Where are you? Okay, so whoever's that, iShell, you, is here are the line profiles that we can resolve with iShell. And so this is kind of some of the interesting features that we can resolve with the spectrograph at 80,000, and which we couldn't resolve with Keck. And so you can get some information about the CO lines that way. This would be 12C16O, and this is the 2 micron band, in fact. So we do see some variation that way. So iShell is a really nice instrument for this work. HL tells this cryonis data, 108% variation in temperature. I mean, this is, and I'll show the summary of all the data, but this is just a few examples. RCRA in 4 months, see up to 34% in temperature changes in the same isotopologue, and 26%. So we're seeing essentially a lot of change in a short period of time. So this is summarizing some of that. Massive YSO variability. So from 2012 to 2014. This may not look like a lot of change, but in fact it is. We're spreading it out over 2 years, so these numbers are telling you how much this is varying. And actually you can calculate that this is 33%, 17%, and 9%. It doesn't look as impressive on this single plot, but it is. Well, I mean, you don't have to be impressed, but it's more than it looks like on the plot. And here you see in this, from 2012 to 2014, high temperature gas changed by 7%, 6%, and 10%. This is gas temperature variability, and this is log, by the way, log space. So that's why it doesn't look as much. But and this is column density. And for HL tau, for example, 7 to 16% variation in column density, and 4 to 100% to 108% variation in temperature. Again, log space here. So we have 67% for low temperature gas for 12 to 13C16O. So a lot of change in a short period of time. And just another, I mean, I don't have to bore you with all these examples, but we do see significant change. 3 years for RNO91, which is a mid-size YSO. a significant amount of change in gas temperature and in column density. Now these were a lot of the data, so some of these targets they weren't observed with the intent to look at variability. So some of the spectra were not exactly the same transitions, but I was able to get column densities to compare. But the idea is moving forward is that you want to use the same instrument and have the same intention, and therefore we can rule out any kind of systematic errors or something due to data sets being different. But this is just a preliminary view of this, and then RY loop, which some of you may know, in 1 year, variability here, and RCRA, which just in a few months, up to 34% in gas temperature, 26% in column density. And then to compile the YSO, both YSOs, for the massive YSOs, we have 46% and for column density variability for low mass YSOs up to 134%, and gas temperature here we have for all the YSOs a significant change. And so, you know, what's happening, we don't know, but we're moving forward with a study to look at using iShell, especially, which is a nice instrument for looking at the massive stars to see if we can see some kind of pattern of some sort, or just see how the changes, if they keep changing in the same direction. And then just to look at isotopologue ratios, so the point here is that the isotopologues are not changing the same in the same target, and we can see this by the isotopologue ratio changing. So for LOMAT, the only isotopologues I had to compare were 13C16O and 12C18O for the same target, taken over different times. And this is not a really meaningful ratio for looking at phenomena, but it is for just looking at how isotopologues might change together or not. And what we see is they don't change together. So maybe there are different pathways happening for these. You know, we might have some CO self-shielding effect here for 12C18O perhaps, or something else going on. But it's not a single pathway for the same isotopologues in that target. And for the massive YSO where I had the data, I had one data point essentially of one target changing by 23% in this isotopologue ratio. Hello. Okay, let's see, we'll just skip that. Okay, so that's the variability, and it's pretty interesting to see how these reservoirs might change and what that could mean for understanding planet formation, and certainly how to incorporate that into models will be a challenge. So as far as the carbon isotope, and you know, when we look at these are all low mass YSOs. This is 12C, 13C again. And when I was talking about the solar system ISM discrepancy in carbon, here's the solar system, here's the ISM, and we see the spread in carbon isotope ratios. These are all a snapshot in time, and we don't have multiple data sets for all of these targets. So how much they probably would change a little bit. Would this change the distribution? I don't know. We'd have to re-observe them. And the issue is, you know, this takes a lot of telescope time, and the overhead is a lot to have to study the variability in something where you have to pound on these targets for a while to get good, precise data. So it's a challenging study to do, to get a lot of data for, and we're probably not going to we're not going to use CRIRIS again for this, but for massive YSOs, it might be a little bit easier to get information on how this might change. But the question is, one motivation for the next phase of this work looking at ice and gas is what could be causing this heterogeneity in 12C, 13C. And one thing we looked at we were talking today a little bit about ice, so I put this in, of how does the CO ice affect the gas abundance in a target. So this would be 12C, 13C in the gas, and how much ice is in these objects. And there's not a really great trend you can see. It's kind of a smattering of data, but we were trying to explore how might ice affect the gas. So you get sublimation from the ice when it's heated through photodesorption, and you can get, and then you get the gas phase. And so could something happen in the sublimation process, or is there some molecular property that's affecting the gas phase? And so we're exploring this. I have an Emerging Worlds grant that is looking at experiments to do this at JPL. And so my co-I, Murti Gudapati, is leading the experiments with two of my undergrads every summer. They do this, and we found, this is year 3 of the grant, and found, this is being, we're submitting this year, hopefully, as a manuscript to see that we actually do they found that, in fact, no matter what combination of 12CO, 13CO is in the ice that they make, 12CO preferentially photodesorbs and is enriched in the gas compared to the ice, and 13CO is enriched in the ice. And the reason for that could be 0-point energy differences. How much energy does it take for 13CO to sublimate versus 12CO? And so the hypothesis is that if we find this, could be 0-point energy differences in the molecules that are affecting the gas phase. So this means that maybe we have an explanation for the heterogeneity in the gas phase, and we have some kind of suggestion of this could be happening in various reservoirs, carbon reservoirs, that you have this preferential holding on to of 13CO in the ice. And what does that mean for prebiotic chemistry? Well, we don't have one explanation on protoplanetary chemistry, but the isotopologues do trace phenomena this way. And so we can say that, photodesorption could be happening to affect the gas phase, so therefore we should consider it as an important component to this early phase chemistry in carbon. And so when we're looking at early carbon chemistry, we're not putting together an entire pathway. That's what's challenging about it, is when we talk about the relevance of all of this, we're kind of looking at these very small steps in the process. And what that means, you remember CO is an early molecule for prebiotic chemistry. And so what that means for later chemistry, the people here who know more about this than I do, is a question. And it's just interesting that maybe we can probe some of this in YSOs to get an understanding of that. And there's a whole astrobiology aspect of this work. And so for oxygen, for those of us who love oxygen, who doesn't, right, is that looking for signatures of self-shielding. So what is this mess of circles, you ask? Well, this is the mass-independent fractionation line again. The mass-dependent fractionation, or 3-isotope plot. This is now in log space to make things more complicated. But the point is that we do see we have three YSOs that one is massive, W3RS5. These are error ellipses, so that some of the data aren't that great. HL tau we published, VVCRA we published, and RAPER 50, which is later in its evolution, we published so far, is that we see a slope 1, they fall on a slope 1 line, and they're enriched in 16O. So that suggests that CO self-shielding may be important in these targets. Again, we're looking at a snapshot. So does this mean CO self-shielding is the end-all explanation for everything? No, it's not necessarily happening throughout the evolution of the disk. It is possible that it's important at this stage and in what we're looking at. And so how does variability factor in? That's another complicating factor. If we reobserve these, would we see signatures of CO self-shielding? And that maybe or maybe not. I mean, I observed HL tau, well, we have data from HL tau from 2010, and they match, we get the same column densities as Sean Britton's data in 2005, so that's a good sign that we're doing, so that maybe there isn't a lot of variability in every single target. But maybe there is a significant amount, or maybe CO phenomena are happening on such quick time scales. But piecing this together is definitely challenging. And remember, this is HL tau, so our favorite disk. Okay, so summary of results. Basically, CO column density for variability. I'm just summarizing the variability now. CO column densities and temperatures vary significantly in massive and low mass YSOs from a few months to years. And so we do definitely find this. They are thus far in our meaning we don't see a correlation in variation in column density going up or down in CO, and then temperature going up or down in that same molecule and that same target. So we can't say it's definitely hotter gas or sublimation or something. We just know that column densities can go one way and temperature can go another way in the same target. So thus far, it's not correlated. And dissimilarity in the isotopologue reservoirs, meaning the isotopologue ratios are changing over time as well. This suggests that there are varying chemical pathways in the YSO. This shouldn't be surprising because, we have 13C16O and 12C18O have different effects in self-shielding, for example. They have different abundances, and so this shouldn't be that surprising, but it is a signature that could be happening. So line of sight variations, this actually should be one, but line of sight variations in stellar companions, magnetic fields, all these different reasons that we talked about before could be affecting CO reservoirs and prebiotic chemistry. short and long-term variability needs to be integrated into models, right? Just we love to say that. And that's hard to do. These we work with a theorist, Karen Willisey. I don't know if anyone knows her, but she's at JPL trying to do disk models looking at the CO, ice, and gas. And it's challenging, even with a simple model, to incorporate all of the components of the model that are necessary. And various interplay between molecular reservoirs could be hinting. This came out of a paper, actually, I was reading about variability, this comment that this could help maybe explain exoplanet diversity. I don't know how exactly, but they made this was an interesting idea to think about, that could we be looking at precursors, signatures of potential, or not signatures, but precursors to exoplanet diversity in the system. That's a big statement to make, so I don't know how we could say that, but this might be another modeling question. And this would be actually conclusions too. So what does this mean for the early solar nebula? Well, reservoirs could vary significantly over the evolution of the disk. And we have large variability in delta 17.0 and initial CAI. So maybe this says something about isotopic inheritance in the solar nebula. Potential complications in interpreting these objects. So we have to be careful how we talk about YSOs as being analogs. They are analogs to some extent, but not necessarily making big, broad sweeping timescale claims over what we're looking at. But they are still important analogs for trying to understand various aspects of chemistry. It just has to be, the interpretation, I think, should be qualified a little bit. So new observations dedicated to variability. So this is what we want to do with iShell, is really focus on variability, so we're not taking different data sets, and make sure we have the exact same band passes and the instruments the same and the reductions the same. That really does help in, because that could change some of these, some of what we see, and we don't want any kind of systematic error, or we want to minimize that for sure. See, there's your donkey. What is this? So anyway, this is the same thing I had up before. Someone asked about my chicken and my donkey. So there it is. Thinking I really want to acknowledge Emerging Worlds for supporting a lot of this research. This is open space in the background. So for moon people, there's a lunar and planetary lab. So I wanted to put some lunar stuff. Really nice data from LRO incorporated in open space. And what's nice about, I will say about open space, is you get all accurate placement of the Milky Way, and the stars are all where they should be. You can change the date. This happens to be July 20th, 1969, which you all know is an important date in history, right, for landing on the moon. So this is where the stars were when the astronauts were there. So anyway, I'll leave the conclusions up there and take your questions. Thank you. So.
Any question for Rachel? Claudia?
Oh, good. Oh yeah, yeah. So I had it on S140. It was just the one with the line profile.
It was, I think.
Yeah. Okay. Okay. Let's see. It wasn't the P Cygni. That was not. That was Keck.
No.
Okay. This one.
Yeah, this one. So I was curious about this, on how you interpret the results, because it seems like you would need the two components really to put the line, right?
Right.
So when you talk about the variability, which of the components is chosen?
Yeah.
Are you using two components?
Yeah. No. So I haven't even analyzed. I haven't even analyzed this one yet. This was just reduced. It's a question of what I would tend to do. So looking at abundances, since I'm trying to get away from, if I'm just looking at a Boltzmann distribution, I would look more at lines like this one and go a little farther out in the spectrum with higher J and not fit this to get an abundance, because some of these are nicer. You do see some variability, but I might ignore this line and use more of a Gaussian. Not all the lines look like this, but the two component, you're right, this should be a two component model. I agree. That's right. And so this is just challenging. And so I haven't really worked with spectra yet. This is the first, so I have to think about how to do it, and I have to look at all of the lines in the spectrum. But I pulled this out like literally right before I got up here to see, because I knew that some of these had these, some of the spectra had these components, but not all of the lines have the components. So if I'm looking for, with the 2 micron, they're usually 12 or 15 nice lines, and if some of them have a 2 component and some don't, you could use the ones that don't and just, you know what I mean, and not, or you're just saying fit all of them with a 2 component model regardless.
Well, I was just asking.
Yeah.
It was striking to me
Well, no, I agree, and the challenge is the challenges with the massive YSOs and now with ice shells. So this is the first high-resolution massive YSO data I have because I've been using Keck, which is more of a, you really do get a Gaussian for the most part for all of the data, is that with these deep, narrow lines with the components, it presents a bigger challenge for getting the abundances the way I was doing it. So I have to consider how to do that and how much. I mean, I actually have to look at all of the spectra and see, but you're right. This one I might not be able to do the way, probably shouldn't do the way I was doing it. And I haven't analyzed this one yet. So.
That perhaps when you have the lower resolution, you might have the two components and not see it.
Correct. Right. But then again, if you don't see it and it doesn't, I mean.
Well, you still don't know which one is varying actually.
Correct. If you're looking at variability, it matters. Yes, because you don't know which one, but that does present a bigger, yeah. So so the better data can be worse.
Can I take another epoch of this data and then see which one is better?
Yeah. Well, we're going to do that. Yeah. It's definitely, yeah.
We'll see.
So you measure the temperature variation.
Mm-hmm.
After looking at the P&R branch lines of CO,
Correct. Yes.
do you ever look at the vibrational temperature between 0 and 1 and 0 and 2?
No, you don't. We don't do it. The row vibrational. Let me see. Where would I be? So the Boltzmann distribution. You're just looking at the rotational temperature. You're not looking at the vibrational change because it's all the same. It doesn't. You're not. We only consider the rotational temperature change, not the vibrational change in the Boltzmann distribution, because you're only looking at that at those lines at that point.
Sometimes the rotational and the vibrational temperatures aren't that well coupled.
Right.
It could be the change in column densities because of pumping.
Yeah.
You've got extra excitation from higher temperatures or whatever, and you're just pumping it up the vibrational manifold, hence reducing your column density within any given vibrational level. I just wondered if you looked at that.
No, because the way, I don't fully understand. I have to think about your question. But in this case, the way the Boltzmann...
Yeah, that's rotational. That's
correct, right. But in the row vibration, so we're only looking at rotational transitions here. This is these from Hytran and all the, the way we don't care. So there's all going from one, they're all in the same vibrational transition, so we don't consider that.
Yeah, I was just wondering if you would ever compare your vibrational transitions to give a feel for that vibrational temperature and see how well it's coupled to the rotational temperature. It might just give you some insight.
Okay, I have to think about that. No, okay. Thank you for mentioning that. I have to think about what that would mean. Yeah.
Kimber?
So, for the laboratory experiment with JPL with the telescope for 13 days before, I was wondering how big of a factor is that in changing the gas phase isotopologue ratio? So, like, if we're using column densities of 13 CO2 or 12 CO abundance, is it something that we should be concerned about, or is it a very small?
Right, that's a question that I've been asking them to. So I'm not in the lab, and these are partial pressure differences, and I've been asking. So the difference, so they'll get like a ratio of 1.6 or to 2 or something like that. How does that translate? Is that what you're asking? How that translates to changes in column densities? Yeah, I agree. That's a question, and we need to quantify that, and that's been my question all along. And so I've been talking to Murdy how to quantify that. So far, I'm not sure how it is. I haven't gotten an answer, to be honest, and I have to think more about that. But that was my first question: is does this mean anything for column densities? It's interesting, and we can say that there's some effect because it's consistent, depending, even when you have an enriched 13 CO ice or an enriched 12 CO ice, you see the same change, and you see preferential 12 CO in the gas. But how does that 1.6 partial pressure difference manifest, how do you translate that? We need to do that. I mean, that is an excellent point, and that's what we need to do. So, yeah, I agree. Yeah.
John, you have a question?
Uh-huh. So I'd be changing. So when I compare those temperatures, let me see which one it might be. When
not that any given system changed that much in temperature, but just the average temperature.
Oh, so like I don't know if this would be the one, but
there's one where you had all of them plotted.
Oh, all of them. Okay, let's see.
And, like that, and so some have very low temperatures, and
Right.
high temperatures, and how do you interpret the different temperatures? Are they gas at very different?
Right. So what this would, when it's taken together, so when I'm comparing, if I say like I'm starting at this point and ending at this point, these are the same target, the same low temperature regime, and the same isotopologue. So I would only compare 13CO at low temperature. So say it's like HL tau. 13CO low temperature regime for HL tau at this epoch, and 13CO low temperature regime of HL tau at this epoch. So it's the same target and the same isotopologue and the same temperature regime. That's how the data. So what?
No, I just meant that when you look at the plot,
Yeah.
Just take a big step back. It's just that with some of the absorption is at very low temperature, like molecular cloud temperature.
Right.
10 degrees or 20 degrees.
Right.
Others are close to the water sublimation temperature.
Yeah.
Like 50
So,
degrees.
right.
Are they where are these absorptions? Are they actually in the same relative space in the different?
Well, they're all different targets, and so sometimes we're looking at disks, sometimes we're looking at clouds, sometimes we're looking at envelopes. So they'd be at different areas of the. They'd be different. Their integrated temperatures are different, and so that's a question of where are we looking? Is that what you're asking? Like.
Yeah. So you said that they could come from very diverse.
Yeah, so if we have a disk or an embedded target, if we get an embedded object and you have like a rotational diagram that's a single line of a cold temperature, it's probably envelope or outer disk. And that would be, low on the plot there. And those do change somewhat, but you're asking of the difference. These are all different targets, and so the higher temperatures would be inner disk material, and the lower temperatures would probably be, that's all the kind of thing we can say is the outer disk or inner envelope. Does that answer your question? Yeah. Okay. Yeah.
Okay, so bringing this back to meteorite.
Whew. No, not my field, but okay.
Sorry.
Yeah.
No, at this point, how do you feel about self-shielding as a model? And do we need another measurement of oxygen isotopes of CAIs at this point?
So with this crowd, I can, freedom to speak. No,
This
it's
is a safe space.
yeah. Is it
recorded?
ever? Yeah. No. So how do I feel about this? It's a funny question to ask in a science colloquium. How do I feel about self-shielding? Well, no. So it's interesting because one of the co-authors of the paper that says self-shielding now happens in the cloud was an author of the paper that said it happened on the edge of the disk. And my question was, how does that person feel about refuting their own paper? And they just, there's like, I don't think they care. And so I think we can say, so my feeling is that if we see a signature of something, all we can say is that it's a signature consistent with this phenomenon. And beyond that, I don't know how we can say much more. That we can't say for sure this is the answer to this isotope anomaly, oxygen isotope anomaly. But it's that we see a signature in disks, so we can say that it could be happening in protoplanetary disks that are like the solar nebula was, probably. So maybe it happened in the solar. I mean, that's all we ever said in the paper. So in 2009, that's what we said. We said this is a signature of CO self-shielding, which is supportive of the hypothesis. Whether it happens in the cloud or the disk is not really my fight. I don't really care, honestly. And some of the arguments that cosmic chemists have, I definitely don't care. I mean, they argue over the 50th decimal place, I think I was saying, of like the age of the solar system. I mean.
Tom, you see self-shielding in molecular clouds on occasion in carbon-13 CN.
Well, but you can't, but the thing with that is that you only have two isotopes. And so you can only say that, the problem, we see it with carbon too, but it's, all you see is an elevated 12C, 13C. You can't make a claim that it's mass-independent fractionation or CO self-shielding because you don't have the three isotopes to plot that. So you can say that it could be fractionation, but the problem with that is that 13CO back reacts, and so you can't, there's no preservation of the carbon isotope effect. And so, whereas with oxygen, it goes into water and silicates, and so you preserve that, and you can make a claim that it's consistent with CO self-shielding in the disk, because you see this in meteorites. With carbon, I've seen the papers where they say, well, a 12C, 13C ratio of a 12CO, 13C ratio of 150 means that there's self-shielding happening in the cloud, but you can't really say that because, and we've looked at this because we had targets that had high 12CO, 13CO ratios, but we didn't see signatures of self-shielding in the oxygen. Because if it's happening, you should see an oxygen effect that you can make a claim for self-shielding, but then, in the same targets where you have elevated 12C, 13C, if self-shielding is the prevailing factor. But we think that it's more likely the ice that could be affecting the carbon isotope ratios in the gas versus self-shielding, because we don't see those connections with the oxygen in the same targets.
This was actually in CN. I don't know what's...
Yeah, I don't know if the CN, right, but you only have 2 isotopes.
Yeah,
And so,
you guys can't look at oxygen isotopes.
right, but if you have 2 isotopes,
Nitrogen isotopes.
if you have 2 isotopes, you can't say that, I mean, you need the 3 isotopes to say it's mass independent. And so that's the problem, is that with self-shielding being a mass independent phenomenon, you can't do that with 2 isotopes. You can suggest it, but that's what Britain had in 2005. So yeah, but CN, yeah, so I'm not, I mean, it'd be interesting to have other isotopes. Certainly it would be great to see the water signature, but there was a problem with the saturation. And so they tried doing that with Herschel, but you get saturation with the H2, it's the H216O.
But another measurement of oxygen.
Oh, so you're asking about that in, yeah, I was thinking, you mean measurement of oxygen in YSOs or in meteorites?
No, in meteorites.
So why would we want to do it again?
Well, not why, but I think I asked, do you think, yeah, do we need any more?
But so the meteorite data, I didn't know that there was, we were missing data for the meteorite measurements in oxygen. Has it not been measured to a significant degree of precision?
Well, that's what I was sort of asking.
I don't know.
I mean, you look at the 3 isotope plot, the slope one line is well defined, right?
Yeah.
We know what the spread is.
Right.
And now you're sort of testing why by doing these observations. So
right.
maybe it's an unfair question to you.
Well, I think the meteorite people can go measure away and argue away. But the thing is that the precision is pretty good with the isotope ratios in the oxygen with the meteorites.
Sure, in the lab.
And it's been met, and we know self-shielding happens in the lab because, you know, the old Van de Schuck and Black. I mean, we know that it's a real phenomenon. I think that we know it's in meteorites, we know it happens, we know it's a realist, it happens, and so connecting that to the solar system is more about a model. And I don't think the YSOs are going to answer this question, because we'd have to get more data for YSOs in any case. We'd have to get more data saying, well, we don't have this, but all disks, if we had all disks showing a 16.0 excess and all envelopes not, for example, you could then maybe say something's going on in the disks, and that's an argument for self-shielding happening in the disk versus the nebula versus the cloud. If you have more evolved objects showing, for, you know, excess, like I'm imagining a scenario, which doesn't happen, but where you have a consistent pattern of where you see the 16.0 excess in YSOs that you can connect to an evolutionary stage. If that would help answer maybe some of these questions. I don't know if we're missing any data on meteorites. I would imagine that if there was any data missing on meteorites, people would be measuring it right now.
Yeah, and I think, what about spatially resolving the disks too?
Yeah, well, the ALMA does that. But the problem is that getting isotope ratios that connect with that to the precision, so you want the observations and absorption to get the precise line of sight, so you can get, you know, model independent column densities. ALMA's in the radio, so connecting those really great maps to the column density is challenging, and the only way I can think of doing it is with temperature, but you need a temperature map. Like if you have, you know, there was a nice map of HL tau, which said 20 Kelvin gas is here in this little region, then you could maybe connect. But we're still integrating along a line of sight with the spectra. So if you had some combination, but right now, I don't know of a way to do it. Yeah.
Carbon-12 enriched in the gas phase compared to ices for other molecules too, or only looked at CO? Is that true?
I'm sorry, say your question again?
Gas phase having higher carbon-12
Yeah.
protein ratio compared to ice phase. Is that true only for CO? Is that all you looked at, or do you or someone you know looked at other similar molecules?
Oh, you mean in the ice phase, solid phase?
Particularly things that could be formed from CO.
Not in the gas. You're talking about ice phase. Gas versus ice, not that I know of. No, the only data we have for 12C, 13C for these same targets is, well, no, I mean, Malam has looked at the paper looking at the various, let me see if I can find it quickly, but when I showed you the oxygen isotope and the carbon anomaly here, those are the molecules that she averaged from the literature. And so that's the gas phase. But in this paper, she determined that was a galactic chemical evolution, that you could explain this line through evolution of the solar system over 4.5 billion years. right? That that the ISM should be lower over 4.5 billion years. You could go from 89 to 65 over 4.5 billion years, 4.567, right? So they found this nice fit that kind of made sense according to galactic chemical evolution of increasing 13C in those molecules. But some of these, I mean, you have to look in then how did they get the abundance. Some of these are radio data. Some of them are big clouds.
These are all radio data.
Not all. They're not. There's some. Was it UV? I don't know. There was. They're older. A lot of these are older papers. So yeah.
That's my paper. So
The Malam. You were on the Malam paper. Oh, I'm sorry. Okay, there.
was my grad.
Oh, good. Okay, so you know.
Those
So
are gas phase measurements. I think we compared it with some of the optical measurements that Steve Fetterman.
yeah.
I think what Chris was asking was, has anyone looked at carbon-12 to carbon-13 ratios on ices like formaldehyde ice?
I don't even know how you observe. Can you observe that in?
I'm
I don't
sure
know.
You could make formaldehyde ice. Isn't that what you're asking?
No, but I mean in using telescopes to look at formaldehyde ice. I don't know. I haven't seen anything. I've looked at. I mean the
Lab
paper.
experiments?
That I don't know.
Okay.
Yeah, that's a good question. I don't know. Looking at you're saying, yeah, there's signatures. I don't know. Yeah, that's a great. The more complicated the molecule, the harder it is to analyze spectroscopically and to get. I know that CO is nice and simple, and then you get, water is a little harder. But certainly, that's not the reason it's not done. But methane would be interesting, and we're trying to. But the problem with a lot of these molecules is you get saturation in one versus the other, and then with methane, you have the Earth's atmosphere is an issue, or there's a spectrograph that can't do it in space, and so for looking at 12C, 13C, and methane, that would be interesting. So yeah, sorry.
Any more question?
It's a good paper. It's one of my favorites, actually. No, really.
Let's thanks again,
Thank
Rachel.
you, Pierre. All right.